Good afternoon, ma'am. I'm Tejaswini from CSO. My seminar topic is laser and holography. So, the full form of laser is light amplification by stimulated emission of radiation. And as per the history of laser, uh, measure was invented before laser, which whose full form is microwave amplification by stimulated emission of radiation by Towner in the year 1939. And some noticeable experiments or inventions in this process of developing laser or stimulated emission by Einstein in 1917, Rubik laser laser by Mymin in California in 1960, in helium neon laser by Alejevan in 1961, and diode laser by Hall in 1962. So let's see the properties of laser light compared to the light properties. Its coherence. That is, the light must be coherent for it to be a laser. Normal light can be coherent or incoherent, but laser light is always coherent. It has high intensity and high directionality and high chromaticity, and because of this itself, laser light is very highly powerful and it is capable of propagating over long distances and is not easily absorbed by water. So let's discuss about the main topics in this chapter: absorption, spontaneous emission, stimulated emission, population inversion, and in optical pumping. So first is absorption. So according to Bohr's law, atomic system is characterized by discrete energy level. That is, here we're taking two energy levels E1 and E2. E1 is ground state and E2 is excited state, and the atom is absorbing an energy of photon energy h mu due to the instance of photon of energy h mu on it, and because of it, it is undergoing excitation. That is, from it's exciting from E1 to E2, and this is nothing but absorption. And so from this we can infer that E equals to E2 minus E1, which is equals to h mu. Now, the rate of absorption depends on number of atoms N1 present in the energy level E1, that is in the ground state, and spectral energy density, which is U or F, which we read as U of radiation. So we can write it as probability of absorption P12 is proportional to N1 U. And to remove the proportionality symbol, we'll introduce the proportionality constant P12 here, that is P12 equals to B12 N1 U. Now coming to spontaneous emission, generally, emission is nothing but the reverse process of absorption. There is the atom getting de-excited by releasing energy. So its emission is divided into two types: spontaneous emission and stimulated emission. So what happens in this spontaneous emission is, without any external effort, the the excited atom gets de-excited by itself. That is, by releasing an energy of h mu. So we can generalize its equation as its probability of spontaneous emission equal is proportional to N2. So we can simply introduce an proportionality constant A21 here, which implies P12 equals to A21 N2. That is spontaneous for spontaneous emission, where A21 is nothing but Einstein coefficient for spontaneous emission, which was introduced by the great scientist Einstein himself. Here we have to note that we get incoherent radiation from heat by light amplification of radiation by spontaneous emission. So using this spontaneous emission, we can clearly cannot obtain laser light because laser light is coherent. Now let's see if it's the case in stimulated emission. What happens in the stimulated emission is, uh, unlike in this spontaneous emission where the atom is getting de-excited by itself, here this atom is made to de-excite by due to heating by another photon of energy h mu, and it gets overexcited, and because of it to again regain its stable state, it goes back to its ground state, releasing two photons, that is its photonic energy and the photon energy of the photon which hit it. So two photons will be resulted in this stimulated emission for one photon of energy which hit our excited atom. So we can generalize it as E equals to E1 minus E2, which is equals to 2 h mu, since two photons are released as output. So the probability of this stimulated emission, that is P 21, uh, to say it clearly, is proportional to U into N2, where N2 is nothing but the number of atoms present in this E2 energy level. So we can to remove this proportionality symbol, we introduce a proportionally constant once again, which is B21. So P21, not P12. P21 equals to B21 and 2U, where B21 is also Einstein coefficient, but for stimulated emission, which is also introduced by Einstein himself. So, like in the spontaneous emission, what we have to note here is one photon of energy h mu stimulates two photons of energy h mu in same phase and direction. Since they are of same phase and direction, we clearly get coherent light, which we can use, which also plays a key role in laser light. So let's see a topic what is about population inversion. So what is population inversion? It is nothing but exciting more number of atoms to higher energy levels than in lower level energy levels, which is nothing but what it makes population inversion. So let's discuss about it. It is a process of increasing excited electrons in higher energy levels, which we discussed just now. So due to this process, what happens is production of laser is possible. Since we discussed before, laser is a light with high intensity. So population inversion plays a key role in lasers. So also, what happens here is, unlike the direct transitions from E1 to E2 or E2 to E1 here and E3, that is, in this case, in this as per this point, E1 is taken as ground state and E3 is taken as excited state. So we're taking a new state E2 here, which is the nothing but called as metastable state. A medium state between these two main extreme states, that is E1 and E2. So what's the difference between this state and the higher energy levels is the electron state remains only in 10 power minus 8 seconds in E3 while they remain 10 power minus 3 seconds in this E2 metastable state. So the electron density keeps on increasing during the increased time in this metastable state compared to the higher energy level. So electron density keeps increasing, which is nothing but on further emissions after the stimulated emission, what will result the output as beams of light with high intensity because of the huge accumulation of energy of electron density here from a stable state, and which is nothing but the laser beam of light which we require and use in this chapter. So let's see the relation between the Einstein constants which we studied before, A21 and B21. Let's once again see the equations we obtain here. That is, P21 for spontaneous emission equals to A21 equals A21 into N2. For stimulated emission, P21 equals to B21 N2 U. And on taking common from these two equations, we obtain U equals to A21 by B21 by B12 N1 by B21 N2 minus 1. And now let's keep this equation aside. Now by Boltzmann distribution law, we know that n1 equals to n naught e power e minus e1 by kt, and n2 equals to n naught e minus e power minus 2 by kt. So by dividing these two equations by n2 equals to e power e2 minus e1 by kt, where e2 minus e1 is nothing but the transition of a energy resulted due to the transition of electrons, which is h mu, which we seen in the before discussion of spontaneous and similar stimulative emissions. So N1 by N2 can be generalized as e power h mu by kt. And on this, substituting this N1 by N2 value in this equation 2, we get this U equals to E21 by B21 whole by B12 by B21 into e power h mu by kt minus 1. So now comparing this to the Planck's radiation formula, that is comparing this Einstein's radiation formula compared to the Planck's radiation formula, what we obtain is B12 equals to B21. We can clearly see because here the value is 1. So B12 by B21 equals to 1, B12 equals to B21. And also we can clearly see that A21 by B21 here is equal to this constant A8 by H F cube by C cube. So these are some important results on comparing the Einstein constants to that of Planck's radiation formula. Now let's see the ratio of spontaneous to stimulated emission from these results. R is nothing but the ratio of spontaneous to stimulated emission, that is N2 81 by N2 B21 U, which is nothing but A21 by B21 into U, and A21 by B21 value which we had here 8 by H F cube by C cube into U. And on generalizing these equations, we get that R is nothing but e power h mu by kt minus 1. And from this equation, we obtain that is the ratio of spontaneous to stimulated emission. We obtain some major important results that is in thermal equilibrium if HF, that is H mu is less than far less than kT, then R equals T per H mu by kT minus 1 is also equal far less than 1. And from this we can derive conclusions that if HF is far less than kT, it is stimulated emission that is valid in microwave region, that is major, which we discussed as a part of the lecture's history. And if HF is far greater than kT, that is spontaneous emission, it is valid in visible region and incoherent region too. Now let's discuss about optical pumping. Optical pumping is nothing but one of the method of pumping of collection of atoms to their inverted states. And apart from optical pumping, other methods used are electrical discharge and direct conversion. Now let's see how this optical pumping plays a key role in our coming experiment, Ruby laser experiment. Let's keep that aside. Now, to discuss the types of lasers, there are three types of lasers: solid laser, liquid laser, and gaseous laser. The main two laser experiments which we discuss in this chapter are solid and gaseous, that is ruby laser and helium ion laser. CO2 laser is also a gaseous laser, but we're not going to discuss about it. Let's come to the ruby laser experiment. So, this is the construction of this ruby laser experiment diagram. That is, we take a rectangular ruby crystal tube in a glass tube, and this glass tube is surrounded by the flash tube coil, a xenon flash tube coil to be particular, which is used for optical pumping, which we discussed before. So if we have to talk about what is optical pumping, it is nothing but it is supplying extra energy to make the atoms in this ruby rod to get excited. That is optical pumping. So here in this is the construction of this ruby laser experiment. Since the glass rod is covering this ruby lasers both ends are converted to partial reflecting mirror, that is 99%, and total reflecting mirror, that is 99.9%, by coating the both sides with considerable amount of silver differently to obtain these two mirrors, which we laser which we use see which we see there used in this experiment later. So what happens is the energy from this flash tube, from this optical pumping, is, let's see this phenomenon clearly in this diagram. Also, the major composition of this ruby rod is Al2O3 plus Cr2O3, which is in the composition ratio of 99.95, 99.05 to 0.05, and uh, clearly the chromium ions are active compared to the aluminum ions. So what happens is, that is after gaining energy from this flash tube used for optical pumping, they undergo stimulative absorbs energy from this, and after reaching the certain energy level of excited state, they undergo spontaneous emission because of the higher energy, which is unstable state, and they reach a metastable state, which we discussed before, where the electron stays for 10 power minus 3 seconds. And here the electrons keeps getting accumulated in this state for 10 power minus 3 seconds, and after that they undergo what is called as nothing but stimulative emission, since they are struck by this energy photons from this optical pumping xenon flash tube once again, and undergo stimulative emission and release what we call as photons, more number of two photons for each photon which struck them. Two photons will be released each time, and these two photons which are released from this stimulative emission, what happens to them is, these two coherent photons gets multiple reflections between fully reflected mirror and partially reflected mirror which we have coated around this ruby laser tube, and on further reflections, what happens to them is their intensity gets increased very highly. And because of this, after a certain point of time, what this gives out as nothing but a light beam of very high intensity, which is nothing but our laser beam of 6943 Armstrong's wavelength, which is the parameter of this Ruby laser experiment laser light. So this is the phenomenon occurring in this Ruby laser experiment. Now let's see what are these applications of this Ruby laser. Ruby lasers have declined in use the discovery of bitter lasing media. Yeah, but they are still used in a number of applications where short pulses of red light are used because clearly Ruby laser is its composition is Al2O3 plus Cr2O3, right? Cr chromium is clearly giving this red color pigmentation of this Ruby laser, which are resulting nothing but red light. Also, holographies around the world produce holographic portraits with ruby lasers inside the sub 2 meter square. That is, for this requirement, ruby lasers are also used. Many non-destructive testing labs use ruby lasers to create holograms of large objects such as aircraft tires to look for weakness in the lining. Ruby lasers were also used extensively in tattoo and hair removal too. But not only in the applications, ruby lasers contain some drawbacks too. That is, their efficiency is very low, and also their output is not continuous, which places a major drawback in many experiments. And also uh, the laser requires high pumping power because the laser transition terminates at the ground state, and more than half of the ground state atoms must be pumped to the higher state to achieve population inversion. That is, population inversion is very difficult to be achieved in this experiment, which is also a major drawback. Also, the defects due to crystalline imperfection. The crystalline is nothing but the ruby crystal which we are using here. So, of course, the crystalline imperfections also play as a key drawback in this ruby laser experiment. Now, coming to the second major experiment in this chapter, that is gaseous laser experiment, that is of helium neon laser. So, this helium neon laser is, as we discussed just now, is a gaseous laser, which is proposed by Ali Jawan, W. Bennett. Now, let's see uh, the construction of this uh, helium neon laser experiment. As you can clearly see here, unlike in the Ruby laser experiment, here optical pumping is not given, but electrical discharge or electrical pumping is used by giving a cathode and anode connections to the end of this glass envelope, and the ruby bore tube is kept inside this tunnel, and we have a high reflector and output coupler here. That is, high reflector is nothing but like how we use partial reflecting mirror surface and full reflecting mirror surface by giving silver coating in the previous uh, ruby laser experiment. Here and here in this experiment we use quartz for as optical resonators. So let's see the working of this experiment using a clear hmm, energy level diagram. Also to say, Al2O3 and Cr2O3 in Ruby laser experiment, which are 99.95 and 0.05 proportion. In this experiment, that is He and E, we use a mixture of helium and neon gases in 10 to 1 proportion. So clearly, He is in major proportion, so it gets electron impact. That is, it gets impacted by the energy emitted from this electric discharge, and it gets excited to measure energy levels, that is E2, E3, and so on, E2 and E3. But while the helium is getting excited, what happens to neon? Since it's in lower proportion, it is getting de-excited. That is, since our neon of the outer orbital shell of 3 number, that is 3s, from 3s it undergoes a spontaneous emission to 2p, and once again it undergoes another spontaneous emission to 1s, but here in this 1s it again gains a metastable state. Now, as we clearly know that in metastable state the electron stays a bit longer as sort of compared to higher energy levels. So after that, due to the impact of energy from this electrical discharge, electrical pumping, once again it undergoes what we call as stimulative emission, which is nothing but gives us two photons for every photon hit on this on these atoms or electrons, which gives 2 photons as an output. And these two photons, like in Ruby laser 2, these two photons undergoes multiple reflection in this part of this construction experiment construction, and similar to the Ruby laser experiment too, due to this uh, due to the population inversion phenomenon here, and due to the stimulative emission of the more number of photons from this high density of electrons, a beam of light of with high intensity, which is nothing but our required laser beam, is obtained in this helium neon laser experiment. So this is the helium neon experiment. This is the how laser is obtained, and the property, the common wavelength of the laser light produced in this experiment is 6,328 Armstrongs. Also, unlike in Ruby laser experiment where we are only getting red light as an output, here we can get various colored lights. That is green color light of wavelength 5430 Armstrongs, yellow orange or orange light of 5940 Armstrongs, and red orange light of 6120 Armstrongs too. And also its advantages are this laser is simply practical and also less expensive. The laser beam is highly collimated, coherent, and monochromatic compared to that of Ruby laser experiment. But here also there is a bit of a disadvantage that its efficiency is low. Its overall gain is very low and typically about 0.010 to 0.1% only. And application coming to the applications of helium neon laser, they are: the narrow beam of helium neon laser is used in this supermarkets to read barcodes, which we see in our daily lives. The helium neon laser is used in holography in producing 3D images of objects. We'll see about holography in later part. So this also plays a key role in holography. Helium neon lasers have many industrial and scientific uses and are often used in laboratory demonstration of optics. It also plays a key role in optics too. So, since we discussed about these two major experiments, that is Ruby laser experiment and helium ionic laser experiment, let's see the common applications of lasers. Laser beam is used to measure distance of sun, moon, stars, and satellites very accurately. That is, lasers plays a key role in this advancement of this major field called astrophysics. It can be used for measuring velocity of light, to study spectrum of matters, to study Raman effect. It can be used in increasing speed and efficiency of computer, which is a key role in our daily lives right now. It is used for welding. It is used in biomedical science. It is used in 3D photography. Other applications are: it is used in communication, TV transformation, and also to search for objects under sea. It is also similar. Actually, it is also a bit similar to sonar, and can be used to predict earthquake. So used in laser tools which are used in surgeries and detection and treatment of cancer. It is used to align straight line for construction of dams and also etc. It is used in holography. It is used in fiber optic communication, which we discussed before. It is also used in military like lidar. It is used to accelerate some chemical reactions. In this way, lasers play a very key role in our daily lives. Thank you.